systems. And I know, like, this is sometimes kids are like, what the what? Coriolis effect, huh? What? Thermohaline circulation, huh? But trust me, this gal was going to be a geologist, so you're in good hands. Let's get started. All right. Plate tectonics. Plate tectonics is the theory explaining the movement of Earth's rigid lithospheric plates. That's the result of convection processes in the underlying partially molten mantle, right? So the plates are moving because there's convection that's spreading them apart or bringing them together due to the result of the molten mantle. This is a little map of our lithospheric plates here on Earth. These lithospheric plates have distinctive features where they either come together, which is converging, pull apart, which is diverging, or push against each other. I'll talk about each of those. Convergent boundaries occur where two plates come together. Features of convergent boundaries depend on the types of crusts that are converging. Oceanic or continental. Oceanic are under the oceans, and continental are under the continents, and their relative densities. Convergent boundaries create mountains, island arcs, earthquakes, and volcanoes. And you need to be able to identify those on a map. So be sure you can identify the geographic examples of convergent boundaries on a world map, like island arcs, volcanoes, and mountains. Island arcs there in the Pacific, Japan down to Indonesia, volcanoes in the Pacific Northwest, and the Andes. Divergent boundaries occur where two plates are pulling apart. Divergent boundaries can result in seafloor spreading, rift valleys, and also earthquakes and volcanoes. Transform boundaries occur where two plates are trying to slide past each other, usually horizontally. They're at an angle, but they're not diverging and they're not converging. They're trying to kind of slide past each other. And they're under pressure. Transform boundaries often result in earthquakes. An earthquake occurs when the stress on these lithospheric plates overcomes a fault that is locked, resulting in a slip and a release of energy. Be sure you can identify geographic examples of divergent boundaries on a world map, like this. Seafloor spreading in the Mid-Atlantic Rift. Yes, I know that circle looks like it's circling nothing, but that's the Mid-Atlantic Rift. And the Rift Valley in East Africa. And be sure that you can identify geographic examples of transform boundaries on a world map. Earthquakes occur. That's the San Andreas Fault, and earthquakes are occurring there in the Himalayas as well. Now, obviously, there's a lot more examples geographically that we could give for each one of these faults, so these aren't the only ones that you could see. I'm just giving a couple of overview examples. All right, let's talk about soil. So it's a jump from lithospheric plates to soil, but soil is really the connection between these abiotic lithospheric plates and the living biosphere that we're going to study. Soil is formed when parent material is weathered, transported, and deposited. Soils are categorized by horizons based on composition and organic content. Yay, soil horizons. So here, this is like a cross section of a soil horizon. We've got our organic layer or O horizon at the top soil, which is our A horizon comes next. I'm going to skip the E for right now. B is our subsoil, and C is the partially weathered parent rock. Not all soils have an E layer. It depends on the climate, and it also depends on the age of the soil, but you might actually see an E layer on the exam as well. Soils are, of course, an important natural resource that must be protected, and there's a lot of questions that pertain to soil health, soil erosion, because soil really is that link between biotic and abiotic conditions. Soil can be eroded by wind and water, and the protection of soil from erosion can actually help protect water quality because soil helps to filter and clean water, ecosystem service. And soil erosion into bodies of water can create turbidity. It can also reduce the penetration of sunlight, which reduces photosynthesis, which of course is the basis of the trophic structure in an ecosystem. And it can clog the gills of aquatic organisms. Y'all, soil is pretty darn important in AP environmental science. So you do a good favor to yourself by going back and reviewing your soil stuff. All right. Different types of soil have different physical and chemical properties. Water holding capacity is the total amount of water that a soil can hold. Different soil types have different water holding capacities depending on their texture, the percentage of sand, silt, and clay, and we're going to get to that in a minute, and their organic content. The ability of a soil to retain water contributes, of course, to agricultural productivity, and we'll talk more about that in Unit 5 tomorrow. Soil texture can affect porosity, permeability, and the fertility of a soil. Hey, it's a soil triangle. Texture is quantified by the amount of sand, bing, down there at the bottom, silt, right-hand side, and clay on the left-hand side, particles that a soil contains. You do need to know how to read a soil triangle. This is in our Unit 4 videos. We'll take you through it. So please, 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 if this is the first time you've seen a soil triangle and your mind is blown, go back and look. The physical, chemical, and biological properties of soil can be tested by various methods. Hint, hint, experimental design. Soil tests can help determine agricultural irrigation needs and fertilizer requirements. There's your soil texture triangle, and it can help you identify the type of soil based on its texture or its percentage of sand, silt, and clay. All right, let's move from soil to the atmosphere. Earth's atmosphere is made of about 78% nitrogen, 21% oxygen, and about 1% other gases, including carbon dioxide and water vapor. This is a little side view of the temperature gradients of the atmosphere. The layers of the atmosphere are based on temperature gradients. The troposphere, let's talk about the troposphere. If you look at the diagram there, the troposphere is the layer that is closest to the Earth. The temperature in the troposphere drops with altitude, meaning it gets colder as we go higher. All weather happens in the troposphere. So if we're talking about weather, we're talking about the troposphere. So your water vapor, your clouds, all the weathers happen in the troposphere. It is also your most dense atmospheric layer because the most particles exist here. The particles of air exist here. The stratosphere is above the troposphere. This is where the ozone layer is located. And you can kind of see this in the diagram. That little straight up and down in the lower stratosphere is where the ozone layer is. But above the ozone layer, the temperature of the stratosphere actually increases with altitude. And you can see that zigzags back from the troposphere. There is very little horizontal or vertical mixing of the particles within the stratosphere. So what goes up there stays up there. And that has some implications when it comes to fluorocarbons and bromated fluorocarbons and all that good stuff. It is less dense in the troposphere. There is less atmospheric particles up there. And we got the mesosphere, and you can see that the mesosphere actually also gets colder with altitude. As we go up, it gets colder. We've got the thermosphere, and finally the exosphere. The exosphere is our least dense, and it fades off into space. The troposphere and the stratosphere are going to be your biggies for environmental science, and you do need to know what happens there. Global wind patterns are the result of differential heating of the Earth's surface by the sun. Yay, global wind patterns. The most intense solar radiation arrives at the equator. This causes surface heating, which leads to density differences in the air. And these density differences lead to our tricellular model of atmospheric circulation. So let's talk a little bit about that tricellular model. So we have this direct incoming solar radiation at the equator, and this warm air rises at the equator, and it condenses and spreads out. And this is due to the rotation of the Earth. Take a look at this picture right here. This is a diagram of a Hadley cell. So you can see there at the equator, you've got really intense solar radiation. That warm surface air rises, and then it spreads out to the north and to the south away from the center line of the equator. The precipitation from this condensation falls between 0 and 30 degrees north and south latitude. That's our latitude for our Hadley cell, right? And that creates a tropical rainforest biome in that 0 to 30 degrees north and south latitude. You can see there that the red obviously indicates warm, moist air, and the blue indicates cool, dry air. So at 30 degrees north and south latitude, that cooler, drier air comes back down to the surface, and that has implications for climate there. At 30 degrees north and south latitude, we find many of Earth's major deserts, and that is because the cooler, drier air from the Hadley cell descends at those latitudes. This pattern of heating, rising, condensing, precipitation, and descent also occurs at our mid-latitudes, those are our feral cells, and at the poles, which are the polar cells. So just a quick reminder, if you can't remember which one's which, here's a little mnemonic. The Hadley happens where it's hot at the equator. Hadley is hot. All right. Large air masses are influenced by Earth's rotation. It's spinning on its axis. The deflection of air masses from a true northward or a true southward path due to this rotation is called the Coriolis effect. Objects, any object, including air masses, are deflected to the right in the northern hemisphere and to the left in the southern hemisphere due to the Coriolis effect, the spinning of the Earth on its axis. The spinning of cyclonic storms, which is counterclockwise in the northern hemisphere and clockwise in the southern, is also the result of the Coriolis effect. All right, we're moving from the atmosphere back down. Watersheds or drainage basins are discrete areas that drain all of the streams and precipitation in an area to a common outlet, whatever that outlet happens to be. It could be a lake, it could be the ocean. This is what a watershed looks like. So we've got rainfall, and you can see that there's lots of stuff going on here. There's a river, there's got groundwater infiltration, there's some farms, there's forests, there's a lot going on here. There's a town. Characteristics of a given watershed include its area, its length, the slope. Does it have a high slope or a low slope? The soil types that underlay it, vegetation types, and divides or boundaries with other watersheds. Watersheds and water quality, of course, are affected by human activities. We're going to actually model this with a free response question today. Incoming solar radiation, which is also called insolation, is not insulation like in your attic, but insolation, incoming solar radiation, is the main energy source for nearly all Earth processes. The intensity of insolation varies by season and by latitude because these factors affect the angle of the incoming rays. All right, so this is a little graphic talking about the angle of incoming solar radiation. So let's pretend that the sun is a flashlight, right? And if you have a piece of paper and you shine your flashlight directly, right, you get a nice round beam of light there. But if you tilt your paper, right, you're going to have an oblique angle there. And so the same amount of incoming solar radiation is going to have to spread out over a greater geographical area. So at any given area, your intensity will be lower. The Earth is a sphere. Surprise, it's a sphere. So the equator receives the most intense solar radiation since it's mostly horizontal to the incoming rays. At each latitude away from the equator, both north and south, the intensity of this insolation lessens. So the poles, north and south, have the least intense solar radiation. The tilt of the Earth's axis causes the seasons. There she blows, tilt. It also determines the amount of daylight and darkness in a particular location during a particular season on Earth. And again, we will practice this today. Along with the intensity of incoming solar radiation, climate in an area is affected by geographic features, and these include mountains and proximity to large bodies of water. Normally, warm surface air rises and cools as it moves up into the troposphere. But we have a phenomenon called a thermal inversion. A thermal inversion occurs when cooler air at the surface becomes trapped by a layer of warmer air above it. Remember that this is all caused by density differences, and warmer air rises, and so that's going to stay on top of your more dense, cooler air. This is a problem because thermal inversions increase the intensity of surface air pollution. It traps the ability of that air pollution to rise up into the troposphere and spread out. And thermal inversions are more common in areas that are surrounded by mountains. So, again, geographic features are going to influence the intensity of your thermal inversions. Talk about rain shadows. A rain shadow is a drier area of land adjacent to or in the shadow of a higher elevation. The higher elevation, like a mountain, blocks the precipitation from reaching this area. And there's a picture. That's the big island of Hawaii. And you can see that one area is very green and lush, and the other side is actually kind of brown and dry. And that is your rain shadow side. So the precipitation is falling on one side, and then all of by the time the air gets to the downward slope, all of its moisture is gone. Ocean surface temperatures help to drive oceanic circulation patterns. Surface temperatures fluctuate in part due to changes in the prevailing winds, which we talked about a few slides ago. So, two things that you need to know are El Nino and La Nina conditions. The El Nino Southern Oscillation, or ENSO, is a periodic, non anthropogenic phenomenon. That means it's not created by man, and it occurs in the southern Pacific Ocean. So, what we would call the normal conditions would be our La Nina conditions. But I don't want to really classify as normal or abnormal because El Nino is just a periodic, naturally occurring event. However, it does cause disruptions. During El Nino events, changes to patterns of rainfall, wind, and ocean circulation occur that can cause significant climatic, environmental, and economic disruptions. So basically, what happens here is the prevailing winds coming off the over the Andes and through the plains of South America weaken. And when they do, they're not able to push this warmer surface water across the South Pacific over to Australia and the Indonesian area. Normally, we've got these strong surface winds that push our warm surface water across to the opposite side of the Pacific. So we've got our cold upwelling that comes from the deeper layers. We've got this thermocline, and our cold upwelling brings nutrient-rich waters to the coast of South America, which helps the fishing grounds there. It also makes sure that warm, moist air that's needed for precipitation across in Australia and the Indonesian area gets pushed over that way, keeps those conditions drier on the coast of South America. But when those prevailing winds weaken, then our thermocline declines. We don't have that upwelling, and our warm, moist surface air gets trapped here over the coast of South America. We have wet conditions, things prone to mudslides there, and then we also have a lack of fishing because those cold, nutrient-rich waters don't come up on the coast. So you do need to know what happens for climatic, environmental, and economic disruptions during an El Nino event. All right, so let's talk about skills associated with this unit. Remember that any skill can be tested in any unit, but there are certain units that lend themselves to certain skills. So practice 1, concept explanation, watersheds. Practice 2, there's a lot of practice 2 in unit 4. We're going to talk a lot about that. Plate tectonics, Earth's atmosphere, global wind patterns, solar radiation and the Earth's seasons, Earth's geography and climate. Practice 4, scientific investigations, soil formation and erosion, soil composition and properties, and finally our environmental solutions, where we're providing solutions and justifying those, El Nino and La Nina.